Hello everyone. Today we're going to have the sampling distribution and point estimation of parameters. This would address the course outcome, apply statistical methods in the analysis of data. At the end of the lesson, the students are expected to explain the general concepts of estimation and estimating parameters of a population or a probability distribution. Explain the important role of the normal distribution as a sampling distribution and understand the central limit theorem. Point estimator. A point estimate of some population parameter theta is a single numerical value theta hat of a statistic capital theta hat. The estimator capital theta hat is called the point estimator. In estimation problems occurs frequently in engineering. The following parameters are some of the variables we use in estimation: the mean, the variance and standard deviation, the proportion, the difference in means, mu1 minus mu2, the difference in two population proportions, p1 minus p2. In estimation, if we want to have an unbiased estimator for this parameter, we use the sample as the estimator of mean. So the point estimator for the population mean, mu hat, is the sample mean x bar. For the estimation of the variance sigma squared, so sigma squared hat is equal to s squared. So we use the sample variance to estimate the population variance. P hat, or the estimator for proportion, is equal to x over n. The estimator for the difference between two means would be x1 bar minus x2 bar, and the estimator for the difference of proportions p1 hat minus p2 hat is equal to x1 over n1 minus x2 over n2. For the sampling distribution of a sample statistic is the distribution of the values of a random sample statistic obtained from repeated samples, all of the same size and all drawn from the same population. Hence, the sampling distribution of the sample mean is a theoretical probability distribution of sample means that would be obtained by drawing from small population all possible samples of same size. The random variables x1, x2 up to xn are random samples of size n. Is the xi's are independent random variables, and b, every x has the same probability distribution. A statistic is any function of the observations in the random sample, and the probability distribution of a statistic is called the sampling distribution. So for example, the probability distribution of x bar is called the sampling distribution of the mean. In central limit theorem, if we are going to consider a sampling distribution of the sample mean x bar, the sample mean is the sample of um, all such means or all such elements. So x bar is the average of all x's divided by n. It has a normal distribution with mean mu of x bar equal to the average of the means, which is mu plus mu plus mu plus and so on and so forth all over n. Take note that they have the same means. And for the variance, since they have the same variances, so the sampling distribution for the variance would be sigma squared of x bar is equal to sigma squared plus and so on and so forth all over n. So, in sampling distribution of the mean, wherein the mean is the average of all the elements, the mean of the sampling distribution is mu is equal to the population mean, and the variance of the sampling distribution is equal to sigma squared over n. If we are sampling from a population that has a known probability distribution, a sampling distribution of the sample mean will still be approximately normal with mean mu and variance sigma squared over n if the sample size n is large. For various textbooks, Montgomery and Runger of Wiley considers n is greater than or equal to 40. But for relatively majority of other textbooks, n is greater than or equal to 30 is sufficient to be considered a large sample. If x1, x2, x3 up to xn is a random sample of size n taken from a population either finite or infinite, with a mean mu and variance sigma squared, if x bar is the same mean, the limiting form of the distribution is z equal to x bar minus mu over sigma over square root of n. So this comes from the standardizing formula for the normal distribution x minus mu over sigma. But since sigma of x bar is sigma over square root of n, so this would now be the resulting formula. So as n approaches infinity, as n becomes relatively large, it approaches a normal distribution. So a non-normal distribution like the uniform distribution for a die, if we will be having a die, and it would be uniform or unbiased die, the probability for each outcome is 1 over 6. All events would be having 1 over 6 as the possible outcomes. While if we are going to consider two dice, the average of the two dice would be different. So the average would be 1 if we have 1, 1, and it only appears once. The average would be 6, would be when we have 6, 6. So this is for 1, 1. This is for 6, 6. This is for 2, 2, 1, 3, and 3, 1. This would be for 5, 5, 6, 4, and 4, 6. While 3.5 would be for 3, 4, 4, 3, 2, 5, 5, 2, 6, 1, and 1, 6. So there would be relatively more possible outcomes that has 3.5 as the average. If you're going to increase the number of samples, it would approach an approximate standard normal distribution. This is as n approach infinity. So a non-normal, a uniform distribution for that matter, if we're going to have an increased number of sample, it would approximately become a normally distributed. So when we are preparing for researches, we tend to increase the number of samples so that if the distribution is not normal, we can assume normality if the sample size approach infinity. Let's have these problems. An electronics company manufactures resistors that have a mean resistance of 100 ohms. So the mean is 100. And the standard deviation sigma is 10. The distribution is normal. Find the probability that a random sample of n is equal to 25 has an average resistance x bar fewer than 95. So for this problem, we are going to consider that it is a chart of normal distribution with sigma of x bar equal to 10 over square root of 25. So 10 over 5 is 2. So we're looking for the probability that x bar is less than 95. So that would be the probability of a z less than 95 minus 100 over sigma of x bar. So that would be um, 10 over square root of 25. So this is a phi of negative 2.5. And we evaluate this probability. So this is 0.0062. So the probability is 0.00621. Let's have another problem. Suppose that a random variable x has a continuous uniform distribution. F of x is 1/2 for x is from 4 to 6. So for this one, it is a uniform distribution which is continuous. So the mean is a plus b over 2. So that is 4 plus 6 over 2 equal to 5. So that's why if it is a uniform distribution from 4 to 6, so it is a normal distribution with mean equal to 5 if we will be having several attempts. While the variance would be b minus a squared over 12. So that would be 6 minus 4 squared over 12. So the variance would be 6 minus 4 is 2 squared is 4. So that is 4 over 12, which is 1/3. If we will be having a normal distribution of size n is 40, so the mean is still 5, but the variance is 1 over 3 divided by 40, so 1 over 120. So the distribution of the sample mean is a distribution with mean 5 and variance 1 over 120. Suppose that a random variable x has a continuous uniform distribution from 0 to 1. Suppose that a random sample of n is equal to 12 observations is selected from this distribution. What is the approximate probability distribution of x bar minus 6? Find the mean and variance of this quantity. So this is a uniform distribution with a is 0, b is 1. So therefore the mean is 1 minus 0 over 2, a minus b over 2. So this is 1/2. While the standard deviation, the variance is 1 minus 0 squared over 12, b minus a squared over 12. So this is 1 over 12. If we will be considering n is equal to 12, so the mean of x bar is still 1/2, but the variance now would be 1 over 12 over 12. So that is 1 over 144. But if we are going to have for the random variable x bar minus 12, the mean of x bar minus, the mean of x bar minus 6 is 1 half minus 6. So that's negative 5.5. While the variance of x bar is 1 over 144. We have to use expected value of x minus a is equal to the expected value of x minus a. And the variance of x minus a is equal to the variance of x. This comes from previous discussions about expectations. Another one. Suppose that x is a discrete uniform distribution with x is 1, 2, 3. So the mean is b minus a, or a plus b. Sorry, this I think is plus. So a plus b over 2. So that is 3 plus 1 over 2 equal to 2. While the variance is b minus a plus 1 squared minus 1 all over 12. So this is 3 minus 1 plus 1. So 3 squared minus 1 over 12. So this is 8 over 12. So a sample of size n is equal to 36 is selected from this sample, and the mean is greater than 2.1 but less than 2.5. That the sample would be measured to the nearest 10. So find the probability that we're looking for the probability that x bar is in between 2.1 and 2.5. So that would be P of 2.5 minus 2 over square root of 8 over 12 over 36, sigma over square root of n, and then minus P of 2.1. So 2.1 minus 2 over square root of 8 over 12 over 36. So that would be P of 2.5 minus 2 divided by square root of 8 over 12 times 36. 3.67, and for the 2.1 it is 0.73. So if we're going to find the probability between this, so 3.67 and 0.73. So 0.23258. (0.23258). Another problem. The amount of time that a customer spends waiting at an airport check-in counter is a random variable with mean 8.2 minutes. So for this problem, we have a mean of 8.2 minutes with a standard deviation sigma 1.5 minutes. These are the data coming from the population. Suppose that a random sample of n is equal to 49 samples is observed. So that means the sampling distribution of this sample would still be 8.2. Mu of x bar is equal to mu, and sigma of x bar is 1.5 over square root of 49. So that's 1.5 over 7. Find the probability that the average time waiting in line for this customers is less than 10. So for letter A, the probability that the sampling distribution of the mean would be less than 10 is equal to the probability that the z value is less than 10 minus 8.2 over 1.5 over square root of 49. So this is equal to P of z less than 8.4. So this is equal to phi of 8.4. So this is approximately almost equal to 1. For letter B, between 5 and 10. So between 5 and 10, so that would be the probability that x bar is between 5 and 10. So this would be a phi of 8.4 minus phi of 5 minus 8.2 over 1.5 over square root of 49. So that would be phi of 8.4 is 1 minus 5 minus 8.2 divided by 1.5 divided by 7. So this is negative 14.9. Phi of negative 14.9. So this is approximately still equal to 1. And for letter C, less than 6. So the probability of x bar less than 6 would be the phi of 6 minus 8.2 over 1.5 divided by square root of 49. This is phi of negative 10.3. So this is approximately equal to 0. So it's up to you to interpret and analyze this problem. So from this problem, you can see that the average is 8.2 with a standard deviation of 1.5. If you would be solving for greater than 10, so it's quite far from 8.2, so it's quite impossible to have a distribution greater than 10. So the probability that it is less than 10 is approximately very, very sure. So it is quite impossible also to have the waiting time less than 6 minutes. So less than 6 minutes is impossible, almost 0. And between 5 and 10 would be sure minus impossible. So that would be 1. For the difference in sample means, if we will be considering mu2 minus mu1, if we have two independent populations with means mu1 and mu2, and variances sigma sub 1 squared and sigma sub 2 squared, and if x1 bar and x2 bar are sample means of two independent samples of size n1 and n2 from these populations, then the sampling distribution of z is equal to x1 minus x2 bar minus mu1 minus mu2 all over sigma sub 1 squared over n1 plus sigma sub 2 squared over n2. So this is approximately normal if the conditions for the central limit theorem applies, and if the two populations are normal, the sampling distribution of z is exactly the standard normal. Let's have an example. A random sample of size n1 is equal to 16. So we have n is equal to 16 is selected from a normal population with a mean mu is 75 with a standard deviation 8. So this is for sample 1. A second random sample for second one um, of size 9 is taken from another normal population with mean 70 and standard deviation 12. Let x1 and x2 be the two sample means. We're looking for the probability that x1 bar minus x2 bar exceeds 4, the probability that 3.5 is that 3.5 is less than or equal to x1 bar minus x2 bar is less than or equal to 5.5. So for letter A, the probability that um, x1 bar minus x2 bar is less than 4 is equal to 4 minus, so less than 4, so this is the x1 bar minus x2 bar 4 minus this is 75 or minus 70 over square root of 8 squared over 16 plus this is 12 squared over 9. So we have phi of, let's evaluate this. This is 4 minus 5. So that's negative 1 over 8 squared over 16 plus 12 squared over 9. So this is phi of negative 0.22, which is equal to 0.41294. For letter B, the probability that x1 bar minus x2 bar is in between 5.5 and 3.5. So that would be the probability that x bar 1 minus x2 bar is less than 5.5 minus the probability that x1 bar minus x2 bar is less than 3.5. So this is equal to phi of 5.5 minus 5 over square root of 8 squared over 16 minus 12 squared over 9 minus phi of 3.5 minus 5 over square root of 8 squared over 16, this is supposed to be plus 12 squared over 9. So that would be phi of 0.11 negative 0.33. So this would give us a probability of 0.17309. So you may consider answering this problem. So for sampling distribution of the mean, instead of z is equal to x minus mu over sigma, we will now be having z is equal to x bar minus mu over sigma divided by square root of n for single sample, and for two samples, x1 bar minus x2 bar minus mu1 minus mu2 over sigma sub 1 squared over n1 plus sigma sub 2 squared over n2. These are the references used to create this PowerPoint lecture.